Hey kids, today we're going to talk about kinetic theory, just reviewing stuff in relation to physical and chemical changes, right? You just watched a video on physical and chemical changes. Your homework tonight will have 4 questions about what's a physical change versus what's a chemical change. Okay, picking those out. You'll also have 2 questions on the effects of heating and phase changes. Okay, and then there'll be 4 questions on conservation of mass. So it's 10 questions, 1 point each, 10 points. I built it in Canvas. It's ready to go. All right, this is back in chapter 16. We actually saw these slides before, right? We're looking at we got a gas, a liquid, and a solid. Okay. Now, if we take a solid, right, and we add heat, we can go from a solid to liquid to a gas and even to plasma. All right. If we remove the heat, right, take energy out, we can go from a gas to a liquid to a solid. Okay? All right. Kinetic theory operates on 3 assumptions: that all matter is composed of small particles. Okay? All matter is in constant random motion. And then particles collide with each other, and in the case of gases or liquids, the walls of their container. All right. Thermal energy, or just think of temperature, is really a measure of the kinetic energy of a sample. All right, let's just skip that slide. Okay, so temperature is a measure of the average kinetic energy of the particles in a substance. The higher the temperature, the faster the movement. So these 3 curves represent the same substance or same sample. Okay, this is the number of molecules. This is the speed of the molecules. The area under the curve would be the same in every case. All right, so at 100 degrees Kelvin, at 100 Kelvin, you've got most of the particles are moving pretty slow, right? At 200 Kelvin, the majority of particles are moving faster. And at 300 Kelvin, they're moving even faster, okay? So as you heat up a substance, the particles are going to move faster, right? Even in a solid, as you heat them up, they're going to move faster. They're going to vibrate. They're going to spread slightly further apart, okay? We call it thermal expansion. If we cool it back down, they're going to move slower and they're going to move slightly closer together, okay? That would be thermal contraction. All right, so keeping that in mind, here's a heating curve for a substance, right? We could call this water. All right, here's time, temperature. We start with ice, right? We're going to heat it up. It's going to reach, for ice, 0 degrees Celsius. Then it will begin to melt. Okay, as it melts, some of it will still be ice in the solid phase. Some will become liquid in the liquid phase. Okay. Now, as it goes through that, the temperature stays at 0 degrees Celsius. Okay, the temperature stays constant during melting. Some will be solid, some will be liquid. But as you add heat, you're converting more of it, okay, from the solid phase to the liquid phase. It actually takes a lot of energy to do that. Okay, and then we can begin, if we continue adding heat, the temperature of the liquid will increase until you reach 100 degrees C. And then again, you'll be stuck at 100 degrees C until you boil all of that liquid. Okay, and during this boiling period, like anywhere in here, some of it will be a gas and some of it will be a liquid. Okay, in a gas, the particles are far apart, right? In a liquid, they're much closer together. Okay, and then you can actually superheat the gas too. Okay, you can heat the gas beyond 100 degrees Celsius. All right, this is the same curve, right? It just shows you here is a solid. This is a liquid solid. Okay, solid and liquid both exist at this range. Here you've got a liquid, okay? Here you've got liquid to gas, okay? And then here you've got gas. If you go backwards, it's called condensation and freezing. You go this way, it's melting and then vaporization, all right? You should already know those things. Okay, now if you want to see a demonstration of this, just go get an ice cube, right? Out of the refrigerator sometime, put it in your hand. You'll hold that, right? Your hand will warm up the ice, okay? And then it'll begin melting. Okay, and of course the ice cube, the part touching your hand, will be getting the most heat, so it'll melt first, all right? But as the ice melts, the temperature will stay at 0 degrees Celsius of the liquid water and of the solid ice, okay? Once it is all melted, then the water will actually begin warming up towards the temperature of your hand, all right? And then once you reach the temperature of your hand, you can't heat it any further, right? Unless you add extra heat. So you'll never boil that water with your hand, okay? All right. Okay, so I just changed presentations actually. This is chapter 16, section 1, part B. Anyhow, again, we saw this slide before, right? Thermal expansion and contraction. A thermometer works, right? As the temperature increases of the air or the liquid you're measuring, what's going to happen is the mercury in the thermometer down here warms up. And as it warms up, it's going to expand up this narrow glass tube. Okay, that's called thermal expansion. Now we can actually calibrate a thermometer to things like, the freezing point of water and the boiling point of water, and we can make a thermometer, right? That's how thermometers were made. Now, if we take this out of the boiling water, it's going to cool down, right? And the mercury will contract and it'll go down. Okay, so we can actually read temperature over a very wide range. Okay, it's also used in things like, right? This was in the ISS room, actually. Okay, remember I took a picture. This little coil right here will expand and contract. It will turn the dial. Okay, when it gets to a certain set point, it'll turn the air on or off. All right, and we also have to worry about kinks and railroad ties and things like that. So we have expansion joints, right, built into railroad tracks. Okay, so that covers thermal expansion and contraction. What happens as we heat something up, right? As we heat it up, the particles move faster and they spread out. Even in a solid, right? They're going to move out, right? The mercury in the thermometer is actually a liquid, okay? The same thing happens like with the rails on a railroad, right? They actually expand. The steel expands, okay? Happens on concrete on roads also, okay? We talked about a phase change, right? These are phase changes from a solid to a liquid, liquid to a gas. Those are called phase changes. All right, during a phase change, you are going to have your mass conserved, okay? The conservation of a mass applies in physical changes and in chemical changes. It does not apply in nuclear reactions, okay, in nuclear changes. All right, we're going to stop. I'm going to switch venues here, and we're going to pick up.